Hi everybody, my name is Cameron and today we're going to be looking at energy transfer, specifically infrared radiation, specific heat capacity, as well as insulation. So let's start with energy transfer. The two words we're going to be looking at is conduction and insulation. Okay, so a good conductor is something that will share or transmit heat and electricity throughout the structure, so with minimal friction. Okay. Insulators, however, are poor conductors. They resist the transfer of heat or electricity. Okay, this can be something like wood, plastic, glass. Okay, whereas a good conductor would be something like your metals. Okay, which is why we make copper pans instead of wooden pans, or why we make copper wiring. Okay, or metal wires. So energy transfer depends on thermal conductivity. So if it's a poor thermal conductor, it's going to be a good insulator. If it is a poor insulator, that means that it's a good conductor. Okay. So some of the factors that will affect how well energy is transferred in a material is the thickness of the material, the temperature difference across the material. Okay, so a greater temperature difference means that there's going to be a greater transfer of energy. Okay, and the thermal conductivity. So the thickness of a material, you can think of wiring. Okay, wires are usually quite small, quite thin. Okay, because the thicker the wire, the more resistance it's going to have as it has to travel through more material. You see, same thing with our pans. Okay, a pan's not going to be super thick. Okay, because the food is never going to get hot enough to cook. So they go make it as thin as possible while still being quite strong. Okay, temperature difference, obviously. If you put a pan in a fire, it's going to heat up, it's going to conduct heat a lot more than if I put it on my hand. Okay, my hand will heat it up, but the fire even more so because there's a greater difference. Okay. To reduce energy transfer, we're going to use materials with a low thermal conductivity, i.e. insulators. Okay, we can also use thick insulating layers. If you look at a lot of winter jackets, they're not thin. It's going to be a lot thicker. Okay, so that energy has to travel through more material, and therefore it's going to prevent that movement out of your body of thermal energy. So let's look at infrared radiation. We've been talking about heat transfer. When something has heat, okay, it is going to be emitting infrared radiation. That's what heat is, okay. So the source of infrared radiation is the sun. Okay, higher temperature objects emit more infrared radiation. So the sun, being the hottest thing in our solar system, is going to be emitting enough infrared radiation to power every living thing on Earth. Okay. Applications for infrared radiation are stuff like thermal imaging or infrared cameras. Okay, so when we see those heat cameras, they're using infrared radiation. They're picking up those infrared wavelengths from an object. And that is also seen in snakes. Snakes are able to see an infrared. Okay, they can see the heat of the mouse or the prey, and it allows it to stand out from the environment that might be cold. But it's not to say that just because a rock doesn't make its own heat, it doesn't emit infrared radiation. All objects emit infrared radiation. Okay, so a black body radiation. This is something that absorbs all radiation. Okay, like the color black. But the best one would be space. Okay, space absorbs all light. You'll see a light ray eventually just disappear into space. Okay, because it doesn't have enough energy to transfer through, and it gets absorbed by the surrounding darkness. Okay, the surrounding blackness. It's kind of creepy, but pretty cool. Okay. Objects with a constant temperature are going to emit radiation across a range of wavelengths. Okay, so that radiation might not just be infrared. Okay, you can have different wavelengths, just like the sun. Okay, the sun, I guess, would be at a constant temperature. Okay, it emits UV and infrared and a bit of radiation, such as, I'm pretty sure, gamma rays. Okay. And the intensity of that radiation emitted will increase for every wavelength. Okay, so what they're basically meaning by this is that the peak intensity is at a shorter wavelength when the temperature is higher. So as the temperature increases, the peak intensity of a wavelength is going to be higher, okay, the shorter the wavelength is. So the shorter it is, the higher the peak intensity. Okay. Okay, so when it comes to temperature and emission, okay, if the temperature of an object increases, it means that it is retaining, it is absorbing more of the infrared radiation than it is emitting. Okay, so what would absorb more of the energy than it emits is your darker materials. Okay, whereas your reflective, shiny, lighter materials would emit or reflect more heat energy. Okay, more infrared radiation. And that's why a lot of the time space blankets, let's say, space blankets are these, you should look it up if you've never heard it. It's kind of like tinfoil. It looks like tinfoil, and they put it on people that are traumatized or people that need to get warm quickly. Okay, it is shiny because it traps in a lot of your body temperature that is being released outwards. You see, it reflects it back at you. Okay, whereas a lot of the time, if something needs to get warmer, okay, let's say you're in a cold climate, okay, and you want to get as much heat as possible, you might want to wear darker clothing, okay, because you're going to absorb as much of the sun's radiation as possible. Okay, now how does this play into Earth's temperature? Well, Earth's temperature is dictated by not by the sun, because the sun's radiation is constant, okay? But it is dictated by the rate of reflection from our atmosphere, okay? So how much infrared radiation is reflected. But it's actually the terrestrial radiation, the radiation from the Earth, that is reflected back down, okay? So if we look at something like Mars or the moon, it has a very, very thin or barely any atmosphere. Okay, so it's going to be very cold. The sun's light comes down, it may be slightly absorbed by the planet, okay, but it then bounces back into space. Whereas our atmosphere and our greenhouse gases are going to reflect that radiation back to the Earth. Okay, it's also going to depend on the rate of emission from, yeah, as I say, the Earth's surface. Okay, so if we look at global warming, okay, as that atmosphere builds up and gets thicker as we emit more greenhouse gases into the air, more reflection of that energy is going to occur, which is going to heat up the Earth. So what is specific heat capacity? Well, the specific heat capacity is the amount of energy required to raise a 1 kilogram mass of an object by 1 degree Celsius. Okay, different materials are going to have different specific heat capacities. Okay, it's going to be a lot easier to raise the temperature of, let's say, a piece of metal than it would be a piece of wood. Okay, it also means that the more mass something has, the more energy is going to be required to raise the entire thing's heat by 1 degree. Okay, and here's an example that we can use to calculate that. Okay. Okay, so finally let's talk about insulation. So we know that we use insulation to insulate, to keep the heat of something in. Okay, so how can we do this? So insulation is going to be made out of specific materials that are bad heat conductors. A lot of the times this could be something like fiberglass. Okay, fiberglass that we use in our ceilings a lot of the time. Okay, this is going to trap any heat inside of the house and keep it inside. Okay, to warm up the house a lot easier. A lot of the time we can also use cavity wall insulation. So in some countries like America, where they don't really use much bricks in their houses, they're going to use something like it's a paper material. Okay, drywall. That's it, drywall. Okay, their walls aren't going to be solid. They're going to have a section, a space in between the wall. Okay, and a lot of the times that space is going to provide insulation. Now they can fill it with something like fiberglass, but that air pocket inside is sometimes also enough to trap in the heat. Okay, and this takes us to the next one of double glazing. So double glazed windows are windows that aren't just one pane of glass, but two panes of glass that have a gap in between. Now that air in between acts as an insulator as well. And finally, we also talked about using something shiny to reflect the heat back in. Okay, so before it was talking about thick, specific types of materials, but something that, like aluminium foil, okay, behind a radiator, is going to reflect a lot of the heat, thus also insulating the entire room. Okay, a lot of the times you'll see in cooler boxes, especially the material ones, the cooler box itself inside will have this reflective shiny material. Okay, and that's going to be trapping a lot of the heat inside of your box. I guess you can't call it a cooler box, those heated boxes that keep your food hot. Okay, so as we see here, just some examples of insulation. We get our double glazed windows. It can go up to triple glazing as well in extremely cold environments, I can imagine. Aluminium foil behind radiators, okay, that's going to reflect a lot of the heat that would have been absorbed into the wall, which would have been a waste. Cavity wall insulation, okay, so the wall might have a little gap in between that is going to be for insulation. And insulation can also be the spray on foam. Really cool stuff. You should look on YouTube for it. It's a foam that they'll spray onto the wall, and the chemical reaction will cause the foam to expand. Okay, and that foam will act as an insulator, keeping a lot of the heat trapped within the house. Okay, my name has been Cameron, and I'll see you in the next lesson.